This video introduces a new dynamic analysis tool called Otter. Otter is designed to aid the translation of serial code into efficient task-based parallel code by analyzing real performance data to recommend specific source code translations. Otter is aimed at domain specialists writing numerically intensive HPC code. The typical workflow of incrementally adding tasks to serial code often leads to disappointing parallel performance with no clear direction for improvement. This trial and error approach is inefficient and provides little insight into the performance of the final application. With Otter, we propose a new data-driven workflow for adding task-based parallelism to serial applications. Here's a simple example showing how Otter can be used. The example program we'd like to parallelize with tasks calculates the nth Fibonacci number using a recursive function. On the left is the original serial code, which contains a single call to the recursive fib function. On the right-hand side is the code annotated with calls to the Otter API. The developer indicates each region of code where parallelism could be applied. Any region of code which can be thought of as a task can be labeled, including any scheduling constraints. For example, inside the main function here, we've wrapped the call to the fib function with a pair of Otter parallel begin and parallel end function calls to indicate this is a region of code where we'd like to parallelize. And the single call to fib inside that has been wrapped in a pair of Otter task begin single and end single calls to indicate that this function call is a task which should be executed exactly once. Inside the recursive fib function, we label each further call as a task. These are registered as children of any enclosing task, and we specify that the enclosing task must wait for these child tasks to complete before continuing with a call to the Otter synchronized child tasks function. After compiling and running the annotated code, Otter produces a report describing the code's performance, as well as a set of recommended transformations. This is a prototype of what the report contains for our simple Fibonacci example. The graph at the top visualizes the task-based structure of the code, illustrating the recursive nature of the program. Execution flows from top to bottom, with nodes representing specific code regions, and the edges representing task creation and synchronization. The overall performance summary shows a collection of high-level performance metrics, which can be selected and tuned by the developer. Next, the report describes the recommended transformations and their location in the original source. In this case, we can see that Otter has recommended that each call to the fib function be wrapped in a task with a cutoff depth of 10 to prevent highly nested, fine-grained tasks, as well as a task wait barrier to suspend the execution of a task until its immediate children are complete. This satisfies the scheduling constraints specified by the developer. Finally, the expected benefit of the recommended strategy is shown. Here, we show the expected speed up. However, the information presented can be configured by the developer. Finally, we'll briefly describe the overall workflow for Otter. The API is designed to be easy to insert into existing serial code, allowing the developer to annotate all source regions which are candidates for parallelization with tasks. Using these annotations, the developer can describe constraints on execution order, such as dependencies between sections of code. Once the developer has annotated all code regions of interest, the serial program can be recompiled and linked to the Otter runtime library. Executing the annotated program then causes Otter to record a trace file containing the relevant performance data for the annotated sections. This trace is then post-processed to determine the transformations that should be applied to translate the serial code into efficient task-based parallel code.